Hello and welcome to part 7 of Dev Maths and Stats Refresher Course, Lecture 3. And here we can look at the concept of elasticity, which is a pretty central concept in many sort of quantitative social science, and also we'll mention comparative statistics quite briefly. So turning to elasticities. We're going back to a previous example here, the example of the impact of different factors on project costs. And what that analysis shows was the greatest impact on overall costs comes from a unit rise in the cost of equipment. After that was staff member and beneficiary numbers was the smallest extra cost. However, there's a catch to this. Imagine that we were measuring the costs in cents. Then the results suggest that a 1 cent rise in equipment price would give a total cost increase of approximately $112. So that's less than the effect of measuring a staff member. So the order of cost seems to change. So that's not very desirable. It's best, if possible, to have a measure of cost influences that doesn't depend on the units. Another example is perhaps instead of measuring employment of people, you could measure the hours you employ people for. And then a 1 unit rise would be even tinier because it would be just a one hour out of a year. So the choice of units shouldn't affect the measure of the order of the impact of costs. So that's a problem with this. Perhaps a more important problem is that from the marginal cost calculations, you can't decide how important the effects are. For example, if the current price of equipment is this, so if currently the unit price of equipment is 2,546, then it doesn't seem unlikely that could go up or down by $1 or more than $1. It seems quite likely. So you have to really worry that this might change by $1 and we're going to have this huge effect on overall cost that we just calculated. However, if the current equipment price was 15 cents, then the chance of a $1 rise would be very unlikely. It's very unlikely to go from 15 cents to $1. Similarly, how significant will those marginal costs be for the project? So what you'd have to do is you have to compare each marginal cost with the overall cost of the project. So you can see that the dollar rise in the equipment price, which I think could go about $11,000 rise, that would be quite important. But an extra beneficiary was $3, and that would not be important. So because of that, instead of the units differences, we often use a measure that relates the relative change in one quantity to the relative change as another. So it gets rid of units and it assesses the relative significance of different effects. And that's called elasticity. So the phrase, the elasticity of variable A with respect to variable B, sometimes called the B elasticity of A, is defined as the change in A divided by the level of A. In other words, the proportionate change in A, or the percentage change in A, if you put it in percentage, divided by the proportionate change in B divided by the level of B. So this is delta A over A. If you multiply this by 100, you have the percentage change in A. If you multiply this by 100, you have the percentage change in B. So it's the same as the percentage change divided by the ratio of the percentage changes. But this conceptually is this is how we conceive it, but actually calculating it, if you change that to this, because this is how you divide fractions, this is simpler for calculation. So it's the ratio of the changes multiplied by the ratio of the levels, but the inverse upside down. So it's change A divided by change B times level B divided by change A. So this is upside down compared to this. Now, as this first part becomes smaller and smaller and smaller, this becomes closer and closer to just the derivative, dA by dB. So we can write, as a precise measurement at a point, we can write elasticity like this, dA by dB times B over A. And that would, just to be clear, that would normally be written in this kind of form as dA by dB and then times B over A. So it's quite easy to remember because this is A over B and this is B over A. Just the opposite. So it's called the point elasticity because it's based on the gradient at one particular point of that graph, A versus B. Sometimes called partial elasticity because you're reminding people that any other variables that are fixed, assumed fixed, because sometimes there are lots of other variables as well. Let's have a look at some examples to try and make it a bit more concrete. Let's imagine you've got a product and the demand for this product is given by this. So there's another product sold in the same market whose price is PC. So P is the price of that particular product that's being sold and Q is the quantity of that. PC is the price of some other product. So here's two questions. What's the price elasticity of demand when P is 6 and PC is 9? Find the marginal change in sales when the price of the other product rises. And what does that show? So price elasticity of demand is given by this. So it's dQ by dP. So what's the comparing the rising Q, the rising Q from a small increase in P is this, dQ by dP, and you multiply by P over Q upside down. So this is Q over P, this is P over Q. So first we need this derivative. So here goes. There's equation 1. So that's telling you what Q is. Differentiate this partially with respect to P. So this is a constant, disappears. This gives you negative 12. This we're assuming is constant because we're partially differentiating, so we get minus 12. And then here, multiply this by P divided by Q. That's minus 12 times P divided by Q. So there's an equation for the elasticity, and then substitute in P is 6 and PC is 9. Oh, we need to substitute in the values of P and Q. We don't know the value of Q. We have to find out what would we sell. So put these prices into the initial equation up here, and we'll find that we would sell 564. So if our price is 6, the other price is 9, we sell 564. So we substitute that Q and that P into here. And you get minus 7 over 47. And as a decimal fraction, it's minus 0.12. This is telling us that a 1% rise in the price of your good leads to a drop in sales of approximately 0.128%. So you'd expect it to be negative. You expect that usually when the price of your good increases, you sell less of it. So price rises 1%, you get a fall in sales of 0.128%. Because this is less than 1%, so the proportionate fall has been less than the proportionate rise in prices, we say that the good is the demand for the good is inelastic. Next question was, what happens if the price of the other good changes? So what's the marginal effect on sales of rising PC? So in that case, we go back to this equation for Q and differentiate with respect to PC, this one, and of course you just find 4, which is positive. That means that if the price of the other good goes up, we sell more of what we are selling. In other words, it's competing with, it's a substitute good. If it was negative, it would be a complement good. And now another example, going back to the project cost function. We want to find an expression for the elasticity of total project costs with respect to staff numbers. So we need to just redefine these because use the equation for something else. So that was the total cost function. And if we're going to find elasticity with respect to staff members, we need to differentiate with respect to L, which we did already above. So that's 0.4 times 150 gives you 60. 0.4 subtract 1 is negative 0.6, which is why you have this here. So that's the partial derivative of Tc by dl. Now, to turn it into elasticity, you multiply delta Tc by dl by this by L divided by Tc, the other way around. So TC over DL times L over TC, as written here. But after doing that, TC itself we can replace because we have the equation for TC. So this TC we replace by here. So it's all of this divided by this here for TC. And the final answer for elasticity is 0.4. So it's just a constant number. So first of all, could you check that this comes out by hand? So check that if you, first of all, how do we get to this? You should first of all be able to do this differentiation, and then you multiply by L divided by TC like this. So when you multiply by L, this times L means that L to the power 1 cancels out with L to the power 0.6, and you get this L to the power 0.4. That's because we multiply by L. Then we divide by TC. So if you imagine all of this is written there. So P to the 0.3 is cancelling out with this. L to the 0.4 is cancelling out with L to the 0.4. This is cancelling out with this. So we're left but with 60 divided by 150. Everything else is cancelled out. And 60 divided by 150 gives us 0.4, because 0.4 times 150 gives us 60. That's how we started. So we get back to exactly 0.4. So you should be able to follow those steps, but even though you should be able to do these steps, you don't have to, because you should be able to look at this and can you predict if this is the elasticity of total costs with respect to employees, L, can you predict what's the price elasticity of cost with respect to beneficiary numbers and equipment price? So this is B to the power 0.5, this is P to the power 0.3. So can you predict what those would be? Just think for yourself, and yes, it is that obvious that the elasticity of total cost with respect to the price of equipment would be 0.3 from here, and with respect to beneficiaries would be 0.5 from here. So this is a very convenient feature of this Cobb-Douglas form, is that when you have a form like this, you can just straight away look and say, okay, this with 0.5 is the one where the biggest possible source of increase of costs is. This with 0.4 is the next most important. This 0.3 is the next. So these numbers turn out to be the elasticities for each of the arguments of the function, which is very, very convenient. Okay, before ending this video, let me just mention comparative statics, which is just another application of partial differentiation. And there's something in problem 8 of the exercises, and it's fairly simple. Whenever you've got an equilibrium or you've solved a particular equation, it could be in any branch of social science or any science actually. So you've found an equation, the solution usually depends on a number of factors. So it depends on all these kind of things. And when you've done your calculation, all that hard work getting to equilibrium, you've taken all this into consideration. And then the problem is that your final solution that you've got, if the values change, then the final solution will change. But if you partially differentiate your equilibrium with respect to these values, you can see how the equilibrium is affected, but assuming that other things remain constant. So say you've done all this, maybe some of these factors are involved, and you found that an equation for the equilibrium price involves S. That's the marginal propensity to save. If you find that differentiating that equation for the equilibrium by the S gives you a positive number, it shows that greater marginal propensity to save would lead to a higher equilibrium price, assuming that all these other factors that might be involved stay the same. So it's a fairly simple concept, but see if it makes sense to you if you look at problem 8 in today's exercises. Okay, so in the next video we'll look at the last part of this lecture, just describing features of functions. For now, thanks for watching.